Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about magnetic cooling or magnetocaloric cooling. So let's dive deep into it. Yes, I have made a video about it few years ago and a lot of YouTubers have covered it, so I'm getting a lot of requests for this. So let's dive deep into it. So problem, basically we need a better and better tool, which is basically heat pump. We need some way to take heat from one place, dump it to another place, and we need to do this as efficiently as possible. So basically you have to understand this. There is no such thing as cold. There is no cold. It's just lack of heat. So how do you create lack of heat? You leach it away. So when you are talking about a refrigerator, it's not cold, it's low heat. So basically the compressor is leaching heat from the inside and dumping it outside. You do it on your house. Basically you take the heat that is inside, you dump it outside, that becomes air condition. So that's what we need, and we need better and better tools. Another aspect is it's one of the most hungriest energy sector that we have to deal with. Basically, you would be shocked how much energy that this puppy is consuming right now. And there is this tiny problem that we call global warming, is that if this keeps continuing on, the amount of energy that is like, back in the days 5%, now it's 10%, no, it will be 50%. So because again, if this keeps happening regularly, it will become unsustainable. To give you a context how hot we are talking about, we are reaching 50 plus degrees Celsius, which is lethal for human body. Meaning if you are outside for long duration, as in like 30 minutes or something, you are serious risk of exposure. And the black parts, those puppies are crossing that, and ultra white parts that you are seeing here, those are 60 degrees Celsius. Yeah, cooked. So if that start to happen more and more, which again, back in the old days, it was rarely happening once in a long while. Now it's happening almost like yearly. So we do have to cool down things. And again, the more temperature delta between the evaporator and condenser, the more energy it takes. The hotter this gets, the more delta becomes higher and more energy we have to burn, which creates a cascading effect. So you have to understand this. Like, this is no longer just like, we can work on it. No. This is like, we need to get it fixed right now. So that's there. And again, it's no longer a aspect of where it's like, it's a good to have. No, it's a necessary to have. Again, I'm coming from a hot place, but be mindful, this is exposing people who are traditionally cold people, basically Western hemisphere. Even they are getting exposed to temperatures that they are not aware of. Like basically, if you say 40 degrees Celsius or 55 degrees Celsius, UK people are not aware of what that means. We Indians, like, we know this. It's like, but UK people randomly that happens, like, what the hell happened? And again, Texan people are like, yeah, our road, it starts to eat our tires. That's how hot it gets. So fundamentally speaking, we need to make sure that we are safe, and well-being of humanity requires air conditioning or heat pump. And food, we're not gonna have food if we do not do that. Medicine, we're not gonna have long lifespan if we don't. And IT. So fundamentally, it does need to happen. And unfortunately, humanity had a very good start. We really got it good going. Then we messed it up. Then we started to use things that punched hole in ozone layer. And given the fact this is happening, I am reasonably sure that you understand that thou shall not punch holes in ozone. So the problem is very significant, like genuinely significant, and getting worse exponentially. Like, this was not there when I made this video, few years ago. So what about magnetocaloric that we are talking about here? Well, it's literally the same thing: compressor, condenser, and expansion valve and evaporator. Now consider this as a 4-stroke system, and this system, basically your magnetocaloric, it's a 2-stroke engine, and it has almost every same things just mapped on overlapping. So when you compress the material, now magnetocaloric material, it's a property of almost all materials. It's just so little that it does not matter. But when you have right alloy, like same way almost everything becomes superconductor if you cool it long enough, be it copper or aluminum. It's just that you want something that does not require it to go absolute zero, like superconductors. Or warm temperature superconductor, that simply means liquid nitrogen is good enough. Same thing here. Magnetocaloric materials are big enough where if you have a thermoprobe, you can detect, hey, temperature changed. So that's the whole point. So we compress it. Now, compressing, it simply means you magnetically domain tight it. Basically, the domains, magnetic domains, are random. So they are chill, they are relaxed. Then you like damn it, compress it. Now this creates a scenario where the heat capacity of this puppy goes down and it starts to dump heat. Now here's the deal. It was on normal temperature, normal ambient. Let's say this was 35 degrees Celsius. It went here and you just like dumped basically compression into it using magnetic field. And again, it's not physically compressed. It's just the domains are aligning. This will like, yeah, it will go hotter than that. It will be like, yo, capacity went up. So from 35, this could easily go to 40 degrees Celsius. At that point in time, you run a basically your hot source, basically somewhere where you are dumping the heat. You dump the heat. Now here's the deal. What happens when you turn off the magnet? You had the magnet, you turn off the magnet. Then it starts to cool down. Why? Because again, you remove that. You created a negative system. And that point in time, you put it into your cold reservoir and it leaches heat away because again, it's below ambient. The moment it takes heats away, now it heats up. Ta-da! So basically, it goes from normal temperature to heated temperature. When it comes outside, it's subambient. You keep doing this again and again, or basically in certain scenarios you have magnets that are spinning and you have materials around it, and all materials are getting exposed to magnetic field and demagnetic field, magnetic field and demagnetic field, and you can keep liquid going from one to another, one to another, one to another. You can cascade it because again, temperature wise these things are not good. When we are talking about compressor puppy, these can easily do 40 or even 50 degrees C T delta, because again my refrigerator has basically evaporator that still freezes ice, meaning it has to be below 0 degrees Celsius. Outdoor temperature, even in indoor environment, when we have loo, we call it in Hindi loo, basically hot heat wave, that puppy can easily be 40 degrees C. So sometimes it requires to create 50 degrees C T delta, and it can do that. This is like, I got you. This will poop itself if it has to do a 5 degrees C. So we have to cascade multiple of them in order to get energy out of it. So that's what you are talking about. Whenever you're talking about magnetic domains, think of it that way, like you're compressing it. Basically, you are changing its entropy, whereas like I can't hold heat, so it dumps heat. You take the heat away and then you like let it out. Once it lets out, it's like, oh, I'm cool. But it's like it's cooler than the ambient. Ambient heat comes into it because to equalize it, and then you repeat the cycle. That's what it happens. And basically dump heat from the outside, then you decompress it or expand it. Basically domain become randomized. It all things happens. It's just like 4-stroke, 2-stroke, 4-stroke, 2-stroke. But be mindful, it does require this very ludicrously hyper over-engineered solution where it's like, how the heck you gonna put something into it which can take the cold away? How can you put something that is warm into it to take the heat away? That's the most difficult part of it, engineering wise. And in principle, let that be very clear, why people are working on it for last 50 years is that in principle, this puppy could be ludicrously efficient because you're not running this giant compression and you're not dealing with phase change. On paper, on principle, on like mathematics level, this should be ludicrously efficient. How ludicrous? Well, think in this way, best COP that you can achieve normally is generally 5. And I'm like being very optimistic. I'm not counting those cooling tower system because again, they are evaporative cooling, not counting that. In a closed loop system, 5 is like you are pushing it a lot. This puppy can touch 6 or maybe even cross that. So that's why people are working on it. So this is the core fundamental. Basically, domains are getting compressed or decompressed. You compress it, it dumps the heat. You decompress it, it absorbs the heat. Nothing more than that. And again, compression, just for better understanding, basically you are changing its entropy of how the magnetic domains are able to absorb heat or dump heat. Now, why do we want to go through that much hassle for last 50 years? Well, due to lack of phase change, again, same thing, everybody will say that it could be more efficient, it could be more. Now, let that be very clear, it could be. It's not efficient as of now. As in 2025, it's not efficient, meaning the best I have seen is 3 COP at T delta of 10 degrees Celsius. Now, be mindful, many research people will use 10 degree Kelvin. And sorry, 10K. So you will be confused, like what, 10,000 degrees? No, it's 10 Kelvin. And that's Kelvin scale is same as a Celsius scale, is just offset to 0. So it's 10 degree Celsius T delta, not huge. Like even my refrigerator is like, bro, like that's not a refrigerator, that's useless. And again, the moment you start stacking it, the inefficiencies pile up at that point in time. Yeah, no. On paper, it's efficient. It's just that nobody has figured out how to actually make it. It's same thing as like fusion. We just 1 year away every year. So on paper, that part does not work. And then we come to refrigerant. This is the another selling point. These are the 2 selling points they will like salesmen will talk about. First, This could be more efficient. Second, this has no refrigerant. So the boogeyman in this scenario is refrigerant. So basically this hole, during 1970s, we detected there is something off going on. Again, we had satellites, we started to notice something off going on. And by the 1980s, we are like, yeah, we punched a hole in that puppy. That's not good. Now, you must have heard people saying that ozone hole is fixed. No, it's not fixed. Like right now, you look into current NASA data, it's still there. It's just the fact is that trajectory is showing that it is healing. So current estimate is by 2040s, it should be very partially filled, and completely fixed should be 2060s. We have made good progress. Like this is one of those case scenario where you had clear communication. What is wrong? Here's the proof of it. This is what we need to do. And we did. Like we started with CFC. We had awesome refrigerants. We just went to poo refrigerants like CFC. That puppy punched hole into it to count, like basically to measure it accurately how much hole punching it has. We call it ozone depletion potential, GDP. Oh, sorry, ODP. ODP. So CFCs were bad, like really freaking bad. So these were counted as one. Then we are like, okay, we have to fix this. So we went to lower harmful gases, which are HCFCs. So basically they had number like 22, 123, 124, 141B, 142B, 225, those sort of puppies. So those have almost like 1/10 the harm, like they are very harmless. Now we are going into third generation of this technology, which is HFCs, which are almost zero when it comes to basically ozone depletion potential. So this part is the first boogeyman. It's like, oh, we do not want to cause harm to the ozone layer. Good. Second is global warming potential. Now, GWP, is it that big of a deal? Yes and no. Yes, you rather should not use a gas that has very high GWP, because there are gases that make CO2 look like a baby. So this earth frying that we are dealing with, people say that it's because of CO2. Yes, and there is a naughty puppy that making it worse. That's called methane, CH4. Methane is 20x. So basically, because global warming is associated with CO2, we marked CO2 as 1. Global warming potential of CO2 is 1. That's the metric. Methane is here. It's like, bro, it's on a whole different level. So even like few tons of methane released in the atmosphere, it's bad. So if everybody started to use methane in refrigeration, yeah, we'd be cooked. So fundamentally, that's why these two things have to be measured. And again, there are many things that have global warming potential, but it's not that big of a deal if it's not too bad. Basically, if it's really bad, like let's say it's 50, yeah, even using tiny amounts are unacceptable. But if it's like 2, 3 or 5, as long as it's below 5, it does not matter that much. But ODP has to be 0, as close to be 0 as possible, like 32, 125, 134A, 143A, 152A, those sort of puppies. So that's why GWP and ODP, both of them has to be measured. And ideally, they should be 0 flammability and toxicity to us. This is how we dug our grave. This is like the reason why this grave exists. Like we had solution of this, but this is how we destroyed ourselves. So this is the benefit of magnetic system. That's the salesperson of it. So first, it could be more efficient. They will say that it is more efficient. It's not. Right now, it's not. Right now, it's a lol. But it could be on paper. And second, it does not have refrigerant. What do they have? They have water. Sometimes antifreeze are added to it. Other than that, nothing else. So these are the benefit of things. Now, can we come to the reality of it? Engineering. Yeah, physics, engineering, economics. Physics, magnetocaloric could be awesome. Physics is like, I got this. People should research into it. The moment you come to engineering, I'm not even touching economics. The moment you come to engineering, it falls apart. Because here's the deal. It's very efficient to move refrigerant because it fundamentally moves on its own. You have a compressor in one place in the loop. You have evaporator, you have condenser. It moves. You do not have to do anything, it just moves. Again, compressor is doing the main work, it moves. So hot is completely separate from cold. It's very easy to insulate. You can make your refrigerator, you can make your air conditioner. Super easy, take it and go. The moment you come into magnetocaloric things, there is no way known as far as now where you can isolate the hot and cold without too much hassle. Like this mixing up is the biggest hassle with this. Like we cannot separate that trigger because again the material is static. You have to go through in or out. So this design is one design where you have that material and you're like, what is this moving back and forth? That is the magnet. Now why magnet is permanent magnet? Yeah, it requires ludicrously high magnetic field. What kind of magnetic field? 1 Tesla. And you're like, hey, that I have heard that Tesla number. Yeah, that's your MRI. General MRIs would be 1.5 Tesla. You can get good MRIs at 3 Tesla, really good MRIs at 5 Tesla. So yeah, it needs that level of magnetic power. So again, if you have to electrically generate 1 Tesla, yeah, bye-bye. So permanent magnet. Thankfully, neodymium magnet is powerful enough to do that. So that's the good part. And here's the deal. You have to physically move the magnet. So again, I genuinely, from bottom of my heart, I'm really angry with all YouTubers who call this solid state. It's not solid state. The only refrigeration system that we have that is truly solid state is Peltier. You can literally have a hot and cool out of it without any moving part, not even a heat pipe if you want to be damn sure it's solid. This is not like, it requires magnetic system moving back and forth. Now you're like, okay, magnet is moving. What about this rod that is going back and forth? That's moving the gas. Because again, fundamentally, this block is heating up and cooling down. So the idea is, when it is in cooling down phase, you push it on this side, the cold loop. When it's on heating side, you put it on this side. So like, yeah, it has too many moving parts. So the block is fixed. You have gas going back and forth, and then you have a magnet that is going back and forth. So this is one design. And then you have another university coming with what we call Brown concept. Now this concept has far better separation. So you have only one magnetic piece that is traveling, magnetocaloric effect. So that is the main block, so to say. So that block is going down. When it's going down, it's the cooling part. When it's going up, it's the heating part. So the separation is super easy. It's just that one tiny effect. This requires superconducting magnet. And they're just showing it. Yeah, we're going to have a superconducting. I'm like, dude, have you seen the cost of MRI? It's like, yeah, we just have superconducting magnet. It's just like, yeah, I can open my refrigerator and here's a superconducting magnet. Like, what the hell? And yeah, be mindful whenever you are looking the research paper of this, they will specify, is the characteristics or efficiency on 1 Tesla or 4 Tesla? Yeah, you need that. And this is another design. On principle, on paper, this is what will be needed in order to run a normal air condition. And like, why does it have so many pipes and manifold? Again, because the material is static. Material itself is heating and cooling. So you need to move things through it. Like in this scenario, gases is moving there. Same scenario, gases are moving there. And again, that should trigger red alert. It's like gases are not that efficient. That's why we have liquid in whenever you're talking about condenser and evaporator. Both, one boils the liquid, one dumps heat, condenses as a liquid. Here, gas. Here, gas only. This, water. Water does allow you to shrink the system. But yeah, the manifold, the plumbing, and again, they will say like, this is like so compact. No, it's not. Because they are not showing you everything else that is needed, specifically the plumbing part. So the moment you put plumbing into it, because again, it has to be like this. That has to be done from one block. It is ludicrously oh, and clean separation is not possible, like how we have clean separation. Like this design is like, okay, this design, again, too many moving parts. This design is like lol. So fundamentally, hot and cool separation is not there. So that itself reduces it, because of the T delta created is barely 5 to 10 degrees Celsius. You have to cascade a lot of them. That's why so many are there. So you're cascading from one to another, to another, to another. Only then you can have enough oomph, enough of a, like, low enough coolant temperature so it can be utilized. And magnets are quite easy to spin. So that's why people are not looking into this design, but in this design, because spinning a magnet, that's like normal thing. Oh, be mindful, the magnets are ludicrously expensive, like ludicrous. They will make your car magnet look EV magnets look like basic. And the material, magnetocaloric, that also have rare earth materials. So yeah, it has a lot of moving part. Like right now, I can take money, I can go into a basically store, and I can buy a refrigerator from multiple brands, be it LG, be it Samsung, be it Voltas, whatever have you. A lot of them on cheaper ones, they just have one moving part. It's called the compressor itself. There is nothing else. And back in the relay is there. Yeah, modern ones have VFD. So that is also not there. So fundamentally, one thing that moves to this. Yeah, no. That's not coming. Like, it works in physics layer. The moment you touch the engineering layer, it falls apart. I'm like, yeah, superconducting. Yeah, we have superconducting magnet on rooftops. And there is only one company, one place I've seen superconductor used as a permanent magnet. That is in maglev, Japanese maglev. They used basically coil, they dumped electrical energy into it, it became a magnet. Because it was superconducting, it was never losing the magnetic, it became a permanent magnet. And then they basically, to cool the helium, they use liquid nitrogen. They have to refill the liquid nitrogen, helium remains always there. So basically the train, once they magnetize it, it remains permanently magnetized for very long duration. Like, I've not seen them ever talking about like how much they have to refill the helium. They only have to top up nitrogen. Yeah, topping up nitrogen in rooftop in India, liquid 9. Yeah, no. I have no idea how the heck people did that. Like, this is from America. I'm like, what the hell? And America is supposed to have some hot places. So how the heck they convince this? So this is the engineering part. That's why it never works from last 50 years. Now let's come to the stupidity of it. So it's the more you look into it, the more you will realize that it's more closer to a tech bro solution rather than actual solution. Like for example, you smoke Elon Musk, and then you'll be like, you know what? Wouldn't it be nice if our car can ride under the road? Like, yeah, man, what can we do, man? What if we drill tunnel and then we had a stuff that we carry on and move to? And people who know things, they're like, bro, you're describing a garbage metro. We have metro. So that's the whole point. Tech bro, it sounds good, it feels good, it's not really good. It's just horrible version of what you actually have. So tech bro, it's like it sounds good. And again, there are genuine use of magnetocaloric system, but those are for quantum computers. Again, they are working on there because helium-3 is very expensive, so they do not want to use helium-3. It makes sense. Let them go YOLO on it. For your normal refrigeration, no, no. So do we have actual tool that can solve our problem? Thankfully, refrigerant is one of those problems that is solved. Second part is COP. The paper COP is not real COP. 10 degree C delta is not good enough to even be a real comparison. Like that's not real comparison. That's like lol comparison. So I have created this chart to give you some context what kind of oomph we need. Right now we have a lot of refrigerant option, 3 major category of them, and all of them have solved all our problems. Ironically, we used to use 2 of them before 1900s. We made a mistake. We switched from them because of some accidents. So ammonia. Now like, wait a minute, I have heard ammonia in 1850s and 1890s. Yeah, that was our first refrigerant. Large scale one, really good one, has no environmental impact, no ozone punching holes, no global warming potential, and it's lighter than air. So if it's an outdoor environment, if it leaks, it will just disappear, and nature knows how to digest it. So you don't have to worry too much about it. So ammonia, no. Now it has a penalty that it is harmful to us. Basically, you can die. So we used to have refrigerators full of this, but then some accidents happen, and people are like no. Now thankfully, ammonia does have one good thing, and because it's a natural system, our nose are very sensitive to it, meaning we can detect it as 3 to 5 ppm. We can detect it like, yeah, and it poofs you at around 300 to 500 ppm. So we can easily detect it. It's almost like how we have LPGs and we put fragrance into, not fragrance, stink into it in order to detect whether it's leaking or not. Same thing applies on ammonia. It's naturally there, and on industrial scale, that's the only way we are cooling big things right now. Right now, if you go into a place, let's say a refrigeration factory for cold drinks, or big brewery, or things, basically things that require ginormous cooling, like hundreds of ton. Yeah, none of them are using hydrofluorocarbons. All of them are using ammonia right now. Now there are certain penalties. Penalty number 1, thou shall not use copper or brass tubing. It must be used stainless steel. So that's the one penalty. Benefit, this has highest efficiency potential. That's why we used to use them. Like this puppy can give you 4.5 COP right now in large scale industrial. And again, let that be very clear, you will find some chiller that have ludicrously high COP. They're like 8 and 9. Yeah, that's because they're using evaporation, meaning they have a water closed, open water loop. It's evaporation. So they are double stacking it. It's not fair. I'm talking about closed loop. So in a closed loop, basically where you're not evaporating or boiling water away, those sort of scenario, this can reach 4.5 COP. That is bonkersly amazing. Like that's like, damn, that is so expensive, so amazing in terms of energy saving, that when you are talking about hundreds of ton of unit, like cooling capacity, it makes sense to pay the extra price that you have to do that. Now, there is some penalties with this. First is that it has to be dealt with trained professional. It's not a lol thing. You have to be a bit mindful around it. So that is there, and you do have to have some exhaust system. But again, people generally installing it dealing with industrial system. There are way more than this than can poof you in industrialist context. So they're good, they're happy. So this is how we are taking care of big loads right now. Zero environmental impact, harmful to us, but again, that makes us very sensitive. And again, we have progressed a lot when it comes to welding and every other things to make sure that this does not leak. So really good system. And then we have basically CO2. So CO2, again, global warming potential of 1, ozone depletion potential 0. This puppy, CO2. Now this has been worked on, especially for India, simply because, again, yes, it is available everywhere, but companies are eyeing India because India is hot and India has money. So people are like, hey, new refrigeration for that. Penalty, it can also not use basically copper or brass tubing, because as you know, liquid CO2 requires ludicrously high pressure. So that puppy requires 130 bar. Yeah, if you do 130 bars in your tubing, normal copper and brass tubing is going poof. So we have to use that. Benefit, this works at hot ambient, meaning the best I have seen refrigerant wise in India is 55 degrees Celsius outdoor temperature. AC is like, I got this, barely. But this puppy is like 60 to 70, is like, I got this, me good, I got this. So all the hotter places are like, yeah, going into this. Texas are going into this. Now be mindful, because of the ludicrously high compression requirement, ludicrously high pressure, 130 bars, if you want to figure out in PSI, just multiply 15. People are like, yeah, this only makes sense for large scale. Nobody has figured out how to miniaturize this hell as of now. And then we come to the best awesome technology we threw away because of our fear, is hydrocarbons. Right now, if you look into good, efficient air conditioning system, almost all of them are using basically hydrocarbon, basically CH4, that kind of thing. Now again, people generally don't use methane unless you are doing Joule Thomson cooling. But if you have seen those ice makers, tiny ones, yeah, they are using this puppy, R600A. That is isobutane. Yes, butane, the lighter fluid. Yeah, fire. It's not an issue. And again, even better than that is propane. Propane can give you 3.5 kind of COP, and T delta is awesome. So you can see ammonia has the best T delta, CO2 has lower, basically COP is also bad, and T delta is also bad. The best is ammonia, second best would be propane, third best would be butane, fourth would be CO2, and then you come to the ugly ones, HFC 134A. So R143A is the worst one. And like, why the heck we are going through this? Yeah, we used to use ammonia. Again, we got scared. Genuinely, we should have jumped to propane, which we did. Right now, many AC systems already have propane. Again, I told you, this is a normal thing. Because, and you're like, what about fire hazard? You have gas pipeline. That puppy has methane. That makes propane look like baby. So it's, and again, in India, we have LPG cylinders in our household, and that has an open flame 1 meter away from it. And we are good, we're safe, we got this. And our cars have what we call a CNG. Yeah, that has 400 bars, so 130 bars is like, bruh. We look at it and we're like, bruh. So we good, we got this, we have the technology. So this are the better solution right now, not future if this or then that, right now. So if you want to reduce your industrial or you want to do district cooling, how would you do that much oomph? Ammonia is your guy. If you're like, hey, I want to have normal refrigeration for my refrigerator that is good, use butane. Right now, many refrigerator in household production is using butane. And you're like, okay, what if I want to reduce the penalty of basically AC? People are struggling with it. But again, that's why I think the names are converted into like R600A and R290A, because again, that number obfuscates the fact that it's a flammable thing. Now, another aspect, people learned it the hard way, that HFC and CFC, they have this one penalty that if your house catches on fire, you rather have this than having HFC and CFC. It's like, why is that? Yeah, figure out what happens when that decomposes. You will rather have CO2, carbon monoxide, and water that is coming out of those things rather than those byproducts. So trust me, we used to start from that. We went like, we started with ammonia, then we jumped into propane and all that. Then we went all the way to random BS things that punched hole in ozone. And then we are like, yeah, that was a dumb idea. Let's come back to ground. So again, do not fall for that. Like magnetic caloric will save us. It's like, bruh, ammonia will save us. I'm not even joking. Ammonia actually is saving our ass. CO2 will save our ass. Propane and butane will save our ass. Not this. And again, I do not like the idea of CO2 one, because again, it's like, COP is not that good. Again, it do make sense for certain places in India where it's like really, really hot. But again, the propane system can work in that sort of temperature, and COP does pile up a lot. So, so that's why it's more of like, tech bro, and people calling, oh, it's a solid state refrigeration. It's like Peltier is solid state refrigeration. Nothing else is. And like, look into how much plumbing they have to do, because again, there is no fluid that is doing the work. The material itself is doing the work. That's the penalty of it. And same penalty applies on that mechanical Coliro system. Basically your rubber band expanding and contracting, that sort of system. Again, that with metal also, and again, that's worse than this design. So that's the whole point. Don't fall for that. Those are like, tech bro solution. Realistically, all you want to do is like focus people into switching to ammonia, switching to CO2 if you are scared of fire, or going into R600A or R290, which we are already doing. So this is a solved problem. We're just like creating a boogeyman and then we are screaming. So this was my presentation on basically the magnetocaloric refrigeration craze that is going on right now. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.